Okay, welcome to Chapter 3, Numerical Descriptions of Data. There's a lot of arithmetic in this section. We're going to be asking our calculators to be doing a lot of that arithmetic for us. The first section covers measures of the center and our M words, mode, mean, and median. We're going to talk about each of these in turn. We're going to start with the mode. The mode refers to the value that occurs most often. And if you've got a frequency table, you can simply look at those totals to find the largest class. If we're looking at a graph, we're talking about the peaks, the highest points. And notice that that's plural. And the reason it is because sometimes when we look at a graph, it could be bimodal or even multimodal. Now, when we're making that distinction, we don't have to have exactly the same height or exactly the same count, roughly the same, and we could conclude that the graph has many modes. So peaks can be plural. When we see multimodal data, it's often a tip-off that there is different types of individuals in the data set with different centers. The mean or the average could also be called the arithmetic mean. And the reason we'll make that distinction becomes very clear when you look at our third project on averages. Often in the media you'll hear, especially on the television, you'll hear people say the average of a rate, and it will be utterly and completely wrong. It will in no way represent the way that that data behaves. So we're going to refer to this as the arithmetic mean. It really is only useful when the data is pretty much symmetrical, and that is when there aren't a lot of outliers. With skewed data, the mean, the arithmetic mean, can be very misleading. So, for example, consider the income of people in this class and then find the average. Add it all up and divide by the number of us, and you'll get the mean income of people in this class. Now, I'm going to illustrate how susceptible that is to an outlier. One data point that's very far from the rest. So imagine that Bill Gates walks into the class, and all of a sudden we're adding all of our incomes, which is a fraction of his, to several 100 million in his case, then dividing it again by all of us as if we have an equal share of that. And all of a sudden our average income has gone into the tens of millions, which isn't representative of Bill Gates' income. It's a small fraction. It isn't representative of our income. So the average can be very misleading if there are outliers, if it is skewed. So let's talk about the population mean, and several things are going on here. First is some new notation. So the population mean is denoted with the Greek letter mu. So what a cat says, right? So mu. Now, mu is the population mean. And remember, we have to make a distinction between these things. There's a population mean and a sample mean. The population mean is all the x's added up. And in an arithmetic class, you'd probably line them up and put plus signs between them. But we're going to do something slightly more sophisticated. We're going to put an operator in front of those x's. And that operator is the Greek letter sigma. It's actually the capital Greek letter sigma. So sigma x in that numerator is telling us to add up all the x's. Now you may say to yourself, I only see one x. And that is a distinction that is sometimes addressed. Sometimes people will put x sub I, where I is the index. In other words, it's saying, take all those x's, whether it's x sub 1 or x sub 2, all the way up to the last x, and add them up. But when there's no ambiguity, when we can put a variable behind a sigma, it simply means take all those x's and add them up. So when we see a capital sigma, that sideways capital M looking thing, we're going to know to add up all those x's. And of course, to get the arithmetic mean, we divide by the number of data points. So in this case, the population size is capital N. So we're going to divide by capital N. So let's say this equation in one go. Mu is sigma x over n. Now, sigma x simply means to add up the x's, over simply means to divide, and mu tells us that we're talking about a population. Now, the sample is denoted with x bar. That's how it's read. X is just our random variable. X bar says that we're talking about the mean of the random variable. We're now not dividing by the population size, we're dividing by the sample size. So instead of a capital N, we're using a lowercase n. So there's how simple it is to compute an arithmetic mean. Simply have to be concerned with adding up all the random variables and dividing by the size of that set. Our third M word, our third measure of central tendency, is the median. The median is roughly the halfway point, so about half of the values are smaller than the median and about half are larger. As a result, it's more resistant to the skewed nature of some distributions. Outliers have less of an effect on it, so it's more resistant to Bill Gates walking into the room. It's frequently used for distributions like income, the example we've just been talking about, or really anything where there's large outliers out there. There's some pretty darn expensive houses out there. So as a result, we might look at the median house costs. Now let's look at how shape affects these things. Notice that in each of these distributions, the mode is right there in the middle. It's the highest point. It's the most likely appearing value. The median is skewed a little bit, and the mean is skewed the most. In other words, the mean is closest to the outlier. It's closest to the tail. It's affected most by outliers, by tails. The median certainly takes the tails into consideration, but is closest to the mode, or closer to the mode than the mean is. Often some things are more important than others, and so they have weights. You're familiar with this when computing scores for a class, and I do this with the weights that I assign to different categories of the course. So, for example, if homework was 20%, worksheets were 15%, and tests were 65%. So here, to compute the weighted average, we simply multiply the score, the data point x, for each of these categories by the weights, and then we add those up. So whatever your score is for homework, you'd multiply that by 0.2. You'd then add that to your score for worksheets multiplied by 0.15, and then add that to your score for tests multiplied by 0.65. Of course, the order of operations means that that multiplication happens before the addition. So we multiply those scores times the weights, and then we add them all up. There's no ambiguity with that because of the order of operations. So when I see the numerator sigma xw, I know that multiplication happens, and then we add them up. Then, of course, in the denominator, we're going to add up the weights. Most people design the weight so they add up to 100%, if 100% is, of course, 1. So we're really dividing by 1, which means we don't have to worry about the division at all. This is assumed to be a sample, so we're going to call it x bar. That concludes our discussion of the measures of central tendency. Now let's move on to discussing the measures of spread. So how spread out the data is. And we're going to again look at 3 different ways of doing that. The first is the range. And the range is simply the max minus the min. You couldn't get anything easier than that. It is, by its design, sensitive to outliers, and that is an understatement. It is essentially telling you about outliers. How far apart are the outermost outliers? So in terms of measures of spread, if we're interested in how far apart the data is in its entirety, the minimum from the max, then the range does a good job with that. It is basically talking about outliers. The interquartile range is the range of the middle half. And as a result, the quarter that's on the right and the quarter that's on the left have less impact on that difference. So it is less sensitive to outliers. That's also a fairly simple computation. We simply find the quartiles and we find their difference, and that tells us the interquartile range. It's like the range in that we subtract to get the range of the middle half. The standard deviation is also appropriate, like the arithmetic mean, for symmetric distributions, and that means that the mean itself is a good measure of the center. It is the most sophisticated way of determining how spread out the data is. So we really do need to be concerned where data comes from, where the source of variation in data comes from, because that variation is key. And really, when we're doing this, we are hoping to find out something. In other words, we're looking for an explanation. And if the standard deviation is useful, then we can talk about individuals within that. But we first have to talk about where that variation comes from. So some things have built-in biases like IQ tests. Some things have genetic reasons for variation, in which case there might be a better use for the standard deviation. So ask yourself, where did the variation come from? And then we ask ourselves, how does that help us understand the shape of the distribution? So looking at a picture can also be very useful. In other words, making a graph like with R, as we did in Chapter 2. So let's talk about the range. So the range is found by taking the minimum and the maximum and subtracting them, and that's great if they are sorted. So sorting the data makes it easy to find the minimum and the maximum values, and very often you can do that with a function. So this is great if you want a quick, rough estimate of variation, but remember, the sensitivity to outliers can be a problem. Now, the standard deviation is interesting in that it is basically answering the question, what is the average unaverageness of this data? In other words, we're going to compute how far away each of our data points is from the mean, and then in a strange kind of way, we're going to find the average of those differences. We're going to find that using a very similar thought process to what you will be doing in the project called averages. So our first way of thinking about this is to ask if we are free of extreme outliers. In other words, some of us may work 2 jobs, some of us may be between jobs, but there's no Bill Gates in the class to throw that mean, that arithmetic mean, very far off to one extreme. So we have to do that because anytime we deal with the mean, we're dealing with something that is very sensitive to outliers. So by extension, the standard deviation is also very sensitive to outliers. So it's not useful when we've got data that is very skewed, but oddly, we can calculate it for any data set. And this is maybe our first look at the idea that you can do something even when the result of performing a calculation isn't very useful. So be very clear that you see this. You can calculate the standard deviation for very highly skewed data sets, but that doesn't mean that the standard deviation is very useful. So what we do is we take each data point in the set and we figure out its deviation from the mean, that is the arithmetic mean or the average x bar. So we need to be a little bit more careful about our notation here because our data points are x's, and of course our mean is x bar. So we want to put a little bit more distance between those two symbols. So if we write out a list of our data points, we've got x1, x2, x3, x4, all the way up to xn. We can talk about any one of them, and by extension all of them, by saying that the ith x, we use I because it's indexed, with the notation x sub I. So the deviation of the ith x, and by extension all x's, is x sub I minus x bar. The deviation, of course, is how far that data point is from the mean. Now, that gives us something interesting, because if we now take those deviations and we find the mean of the deviations, and by that I mean the arithmetic mean, just the one that we talked about at the very beginning of this chapter, and we add all those deviations up, well, by definition, by the way that we created the mean, there is as much above as below. There may be one single large value above and lots of little values slightly below. But regardless, if we added them all up and then divided by the sum, we would always get 0. So that puts us in an interesting situation. The standard deviation is supposed to give us the average unaverageness. In other words, we want to do something to those deviations so we can talk about their average. How far, on average, is a data point from the mean? So we need to do something different than simply add up all the deviations and divide by n. And we do something very similar to what you're going to be doing in the project. So the first thing that we do is we square the deviations. We square the deviations to get rid of the negatives, that is the lefts and the rights of the mean, so they can be added up, and that'll calculate a kind of average. But the moment that we square something, we've made it times itself. We've made it larger, or if it's between 0 and 1, smaller. All sorts of stuff falls into play. At some point, we're going to have to take the square root. Now, there's other reasons to do this. Squaring also has some nice mathematical properties. Remember the graph of y equals x squared. It's a nice, smooth graph. And again, it rewards being close. So when you talk about squaring, we often think squaring makes things bigger, and that's certainly true for numbers further from 0 than 1. 1 squared, of course, stays put. 2 squared becomes 4. 9 squared becomes 81. They grow nice and fast. But remember what happens if you're close to 0. That is, if the deviation is relatively small, between 0 and 1. It actually gets smaller. So that's what we mean by saying rewarding being close. In other words, rewarding being close to the mean. That actually gets smaller when we square it. Now, you might think we're going to divide by n, but we want to kind of overestimate the standard deviation, so we're going to divide by a number that's 1 less. We're going to get a bigger number as a result for our standard deviation. We're going to divide by 1 less than the count. It makes it a little bit bigger, a little bit larger, and we call this variance. So what have we done? We found the mean of the population, and that means that that's only useful if the data is relatively symmetric, if there aren't a large number of outliers, if there's a single mode. Then we've taken that mean and we've subtracted each of the data points by it. We've then realized that we can't take the average of those deviations, or we'd just get 0. So we've squared those deviations. They're now all positive, or 0, and we've rewarded being close to the mean. This we then divided by 1 less than the count, and that's called variance. Now, at this point, you should say to yourself, well, we squared these numbers. Whatever the units were, they're completely different. If you're in the sciences or medicine, you know you can't just go around squaring things. Division does not undo squaring. We've still got unit issues. This is called the variance, and you're often asked for the variance, and the calculator will give you the variance. But we are still interested in getting the standard deviation. So what is the variance? The variance is the average squared deviation. We're using that word average loosely, and we will continue to do that over the course of the semester. When we say average, we don't always mean the arithmetic mean. Now, you can think of this as the last thing you get before you take the square root, because in our next step, we're going to take the square root, and that is going to give us the standard deviation. Notice that this also tells us how the variance and the standard deviation are related. If you take the square root of variance, you get standard deviation, so you can undo that. If you square the standard deviation, you get variance. So let's look at this in our calculator. So the standard deviation, we take the square root of the variance to get the standard deviation. It's denoted capital S, or if there's lots of different variables running around and we need to distinguish x's from y's from z's, or if we're using variables that are more unique to the data we're looking at and have lots of them, we're going to call it S sub x if the standard deviation is of the x's. So there's everything put together. Let's talk through each step. The x sub i's are simply each of those data points, and if they're each of them, they're all of them. We then subtract the standard deviation from that. So for each of those x's, we subtract the standard deviation. That's the deviation. We then square the deviation. Once we've squared the deviation, we no longer have negatives, and we've rewarded closeness. We then add up all those squares, and that's our numerator. That's the majority of the work. The next step is to simply divide by one less than the total, one less just to make that quotient slightly bigger, and then we take the square root to undo the square, and that gives us the standard deviation. Notice that we're assuming that this is a sample standard deviation. So we have an S, just like we used X for the sample and we used mu for the population when we were talking about means. We're now using S for the sample standard deviation. The population standard deviation is denoted with a lowercase sigma. So if you're thinking to yourself, wait, this has two sigmas running around in it, and that's true. The lowercase sigma is used to denote the population standard deviation. And remember, the capital sigma is used to denote that operator of adding up all those deviations. And also notice that when we've got everything, when we are talking about a population standard deviation, we don't need to divide by one less than the count. We simply divide by n. That's the only other difference. Capital N, of course, being the population. Let's talk about how to do this on our calculator. If you go into a list and you load some data, so if you wanted to get out your calculator now, go into a list and load the data that's on the screen, 6.8, 8.2, 7.5, 9.4, 8.2, and 6.3. And then go into the stat menu and calculate. We're going to do one variable statistic, so that's number one, then press enter. On your screen, you'll see that you're doing one variable statistics. You might have to load L1, that's in the list menu again. And then when you press enter, you can see that two screens appear. That downward pointing arrow in the bottom left means that you've got more information. And there is a lot of information here. So let's take a look. X bar is the arithmetic mean. That's assuming that this is a sample. So that's 7.73 repeating. The sum of the x's, sigma x, just said what would you get if you added them all up. The sum of the x's squared is the next piece of information. S sub x is the sample standard deviation, treating n as if it was a sample, so in the denominator n minus 1. Sigma sub x, treating this as the population standard deviation, so just dividing by n. There's our n equals 6. The minimum x value, 6.3. The first quartile is at 6.8. And then looking over at the second screen, we can see that the median, that is the second quartile, is 7.85. The third quartile is 8.2. And the maximum value that we entered was 9.4. Now, that's great. And you might say to yourself, well, all this requires the data set to be relatively symmetric, and that's definitely true because the mean has to be useful. So let's get our first mathematical result about statistics. So this is when we start to talk about what we know simply because of the way we've defined things. Because of the way that we've defined the standard deviation, certain things have to be true. And here's our first mathematical result based on the definition of the standard deviation. This works for any set of data. It's a theorem, which means that it can be proven simply by using the definition of the standard deviation. It requires a lot more work than that. This is actually a calculus result, and it's one of the first results in statistics about statistics itself. In other words, we can start to use much more sophisticated ways of talking about statistics than simply doing arithmetic. and Chebyshev's theorem is an excellent example of that. I'm going to say again, this works for any set of data. What that means is we don't have to worry about whether it's symmetric, whether the mean is representative of the central tendencies. We can simply say, if you go through and do this arithmetic, these are the results you're going to get. Now, let's take a look at the first result. It says that at least 75% of the data fall in the interval from mu minus 2 sigma to mu plus 2 sigma. So notice that that has promised a lot. This theorem's saying that for any set of data. But now it's asking us to already know the population mean and the population standard deviation. In other words, that's not x bar and s sub x. That's mu and sigma. So if we know the population central tendency, mu, if we know the population variance, how much it is spread out, sigma, then we can make an excellent claim that within 2 standard deviations of the mean, 75% of the data falls. Now, let's go back through and just quickly talk about the arithmetic of why we say that this means within 2 standard deviations of the mean. So that first endpoint where we start is mu minus 2 sigma. That's 2 standard deviations to the left. And we end our interval 2 standard deviations to the right. So we say within 2 standard deviations of the mean. Really, there's 4 standard deviations here, 2 to the left and 2 to the right. But we can say within 2 standard deviations, we get 75% of the data. Remember, this is true for any data set, assuming that you know the population mean and the population standard deviation. And of course, once you've got one of these results, you can use the same techniques to get more. Within 3 standard deviations of the mean, we get 88.9% of the data. So 3 standard deviations to the left of the mean, 3 standard deviations to the right of the mean give us about 89% of the data. 4 standard deviations of the mean, and I should say at least 89% of the data. Within 4 standard deviations of the mean, 4 standard deviations to the right, 4 standard deviations to the left, we get at least, often much more, 93.8% of the data. Now, that leads to an interesting question, and that interesting question is measuring data based on its distance in standard deviations. In other words, if I say that a data point is 2 standard deviations from the mean, I can shorten that and refer to that as the z-score. The z-score simply tells us how far data is from the mean in terms of standard deviations. So you simply take the distance between the data point and the mean and you divide it by the standard deviation to get the z-score. That's exactly what it means to count something in terms of something else. So what is that? That is a measure of unusualness. And it's a standardized measure of unusualness because it's divided the units of whatever the data is by that standard deviation, which, remember, still preserves those units. So when we talk about the z-score, we can talk about how unusual a data point is. If something's z-score is 0, it is the mean. If something's z-score is 1, then it's 1 standard deviation to the right of the mean. So the z-score answers the question, how far is a data point from the mean? If the data value is outside 2 standard deviations of the mean, that is, the z-score is either 2 or negative 2, then we say that the number is uncommon. So a standard deviation of 3 would be outside of that. So outside meaning out in those tails. To the right of 2 standard deviations to the right, to the left of 2 standard deviations to the left. Now let's talk a little bit about ranking. Let's talk about the words that go with these. If we divide the population into hundredths, we're dividing it into percentiles. Tenths is deciles, fourths is quartiles, fifths is quintiles. So some nice vocabulary there. Quartiles divide the data into fourths, and that's easy to do. So once we have the data in increasing order, we can find the median. The median divides the data into two halves. And if we do this again for each half, in other words, if we find the median of the data below the median, we can call that the first quartile. That's divided the data into 25% below and 75% above. So that's 1/4. If we then find the median of the data above the median, then we've found the third quartile. That tells us that 75% of the data is below that. Now, the median could be called Q2 as a result. In other words, it divides it into those halves. The second quartile means that there's 50% below. But we generally refer to that as the median and not as Q2. Q1 is the first quartile. Q3 is the third quartile. The interquartile range is our last measure of variance, of the spread of the data. And the interquartile range is simply Q3 minus Q1, the third quartile minus the first quartile. It is resistant to outliers in much the same way that the median is resistant to outliers when we are interested to express the center. Now, once we have quartiles, we can talk about a better definition for an outlier. So we can create fences. That is a boundary. That is an interval in which we say those aren't outliers. So we only refer to outliers as being 1.5 interquartile ranges below the first quartile or 1.5 interquartile ranges above the third quartile. So if you're outside of that, then you're considered an outlier. And the last thing that we're going to look at is a box and whisker plot. The neat thing about a box and whisker plot is it allows you to compare distributions very easily, assuming that the axes are the same. So a box and whisker plot is a way of showing a 5-number summary, and the 5-number summary goes from left to right. It's the minimum, the first quartile, the median, the third quartile, the maximum. It's shown with the interquartile range from the first quartile to the third quartile as a box. Looks like a diode diagram to me. The median has a bar down the middle, and then the whiskers go off to the minimum and the maximum. So that's the way a box and whisker plot looks. A box and whisker plot is excellent for gauging the symmetry of the data. In other words, you can see how close to the median of the box or the middle of the box the median is, and how symmetric the two whiskers are off to the minimum and the maximum. And as a result, you can quickly get a look at the spread of the data. Now, we like box and whiskers plots because it allows us to compare data quickly and easily. So we can compare two different distributions if we plot them on the same fields, and then we can see where the majority of the data lies in each. And there's questions like that in your homework.